Hello students, welcome to 18th lecture of structure of atom. In previous lecture we discussed about shape of atomic orbitals, and now in this lecture we will start with energies of orbital, and then we will discuss about some rules of how to arrange electrons in these orbitals. So as mentioned earlier in quantum numbers point, principal quantum number mainly represents distance of electron from the nucleus and energy. As the principal quantum number increases, distance of electron from the nucleus increases, as well as energy of orbitals also increases. Thus, the energy of orbitals in the hydrogen atom increases as follow. So, all the orbitals are arranged in increasing order on the basis of their principal quantum number. So, as the principal quantum number increases, energy increases. Similar quantum number containing orbitals will have same energy in case of hydrogen. We are talking about hydrogen only. So, for hydrogen, arrangements are mentioned. So as we can see, 1s orbitals have less energy than 2s orbitals, and 2s and 2p both of them have same amount of energy, and this trend is observed throughout this representation, and it is depicted in figure 2.16. Although the shape of 2s and 2p are different, and electrons has the same energy when it is in the 2s orbital as it is present in 2p orbital. Okay, so in this case shapes doesn't matter. Okay, we are talking about hydrogen. It contains only one electron, so unielectronic species has no relation with the shape of orbitals. Energies only depends on principal quantum number. So we can say that it depends on distance. As the principal quantum number increases, distance also increases. So now the orbitals having the same energy are called degenerated energies orbitals. So all the orbitals of 2s and 2p, that means we have one orbital in 2s and 3 in 2p, px, py and pz. So all of these four will have same energy. Same thing can be applied with third principal quantum number. In third principal quantum number we have one s orbital, 3 p orbitals and total 5 d orbitals. That means we have 9 of them. So these 9 orbitals have same energy, and that's why all of these 9 are called degenerated orbitals. Okay, so as you can see in this figure, in representation, 3s, 3p and 3d, all of them have same energy, so they are called degenerated. But this is true for hydrogen only. Now let us move further. The 1s orbital in the hydrogen atom, as said earlier, correspond to the most stable coordination condition, and it is called ground state. When electron of hydrogen is present in 1s orbital, it is called ground state configuration for hydrogen, and if it is present in any other than 1s, then it is called excited state of a molecule or atom. So, and the electron residing in the orbital most strongly held by the nucleus because of less distance. As the distance decreases, attraction becomes stronger. An electron in 2s, 2p or higher state orbitals in hydrogen atom is in excited state. Now here representation of orbital is mentioned. First let us concentrate on figure 2.16a. So as you can see, 1s orbital has lower energy than 2s and 2p. 2s and 2p both of them have same energy. 3s, 3p and 3d all of them have same energy, and as you can see, for s orbitals only one dash is mentioned. It represents it has only one orbital. For p you will see 3 dash. It represents we have 3 orbitals, px, py and pz. And for d obviously you will see total 5 dashes, dxy, dyz, dzx, dx square minus y square and dz square. So for first representation we have same energy for same principal quantum number, and figure 2.16b represents multi-electronic species. That means species having more than one electron. So here situation is slightly different. As we can see, similar principal quantum number do not represent same energy. In this case, principal quantum number and energy, they are not connected anymore. So as you can see, 1s has less energy than 2s, but 2s is less than 2p, and 2p is less than 3s, 3s is less than 3p. Then something odd is being observed. 3p is less than 4s, but 4s is less than 3d. That means principal quantum number 4 has less energy than principal quantum number 3. Okay, so why this type of situation occurs, we will discuss it. So now next discussion is about the energy of electron in multi-electronic species. So unlike the hydrogen atom, now if you have more than one electron, then energy also depends on azimuthal quantum number or subsidiary quantum number. That means in uni electronic species, energy only depends on principal quantum number n. But if you have more than one electron, then L value or azimuthal quantum number also contributes or participates in energy deciding factor. So let us discuss about it, and how can we identify energy of electrons by the given principal quantum number and azimuthal quantum number. So as mentioned earlier, for principal quantum number, increasing principal quantum number represents increasing energy. Same is applicable with azimuthal quantum number. Increasing azimuthal quantum number value represents increasing energy. Now we know that L is equal to 0 represents s orbital, 1 represents p, 2 represents d, and 3 represents f orbital. So increasing L value represents increasing energy. So s represents least energy, then we have p, then d, and then we have f. So lowest energy from all of these four will be from s, and highest energy will be from f orbitals. So we have to use combination of n value and L value, that means principal quantum number and azimuthal or subsidiary quantum number. So energy of these orbitals on the basis of L value are represented here. As you can see, s is less than p, p is less than d, d is less than f. So initially effect of this azimuthal quantum number is not observable, but as we move to the higher energy levels, its effects is observable. That means L value also affects the increasing energy or decreasing energy factor. As a result, you may see example like this: 4s has less energy than 3d, 6s has less energy than 5d, 4f is less than 6p. Okay, so these type of factors are observed due to the effect of azimuthal quantum number. The main reason for having difference energy of the subshell in the mutual repulsion among the electron in multi-electron atom. Okay, so main reason is repulsion between the electrons. As mentioned in initial stages, initially in this unit, like charges repels each other and unlike charges attracts each other. So because of this, like charges, that means electrons repels each other. In same orbital, if you have large number of electrons, then obviously they are going to repel each other, and that's why energy increases. So as we know, in s orbital maximum possibility of electron is 2. In p orbital we have 6 electrons, in d we have 10, and in f we have 14 electrons. So as the number of electrons increases, repulsion also increases, and it increases the energy. So least number of electron is present in s orbital, only 2. That means least repulsion will occur. On the other hand, in p we have 6 electrons, so 6 electron will repel each other. That means comparatively higher repulsion and higher energy. In case of d, 10 will repel each other, that's why even more energy will be observed, and in case of f, 14 electrons are repelling each other, that's why it will be highest in energy. And n value directly represents increasing energy. Okay, and same thing is applicable with L value. Increasing L value also represents the increasing energy. So now let us move how to calculate or how to arrange these orbitals in their increasing energy. Before that, as mentioned, in case of hydrogen we have only one electron, so no electron-electron repulsion occurs. That's why it only depends on principal quantum number. So in hydrogen only produced attraction is between the nucleus and electron. In other multi-electronic species we have that attraction, that means between nucleus and electron, but we also have electron-electron repulsion. So it is also factor affecting energies. Thus the stability of electron in multi-electron atom is because total attractive interactions are more than repulsive interactions. In general, the repulsive interaction of the electron in the outer shell with the electron in the inner shell are more important. That means electron present in lower principal quantum number are more important than electron present in higher principal quantum numbers. If nuclear charge of proton or nucleus increases, that means more positive charge will be filled inside the nucleus, and that's why more stronger attractive interaction will be observed between the protons and electrons. So attraction towards the electrons increases. So Ze represents positive charge on the nucleus. Due to the presence of electron in the inner shell, the electron in outer shell will not experience full positive charge of the nucleus Ze. So representation of a given statement: at the center we have positive nuclear charge. This is inner shell having lower principal quantum number. This is outer shell having higher principal quantum number. So let us call this inner shell as I and outer shell O. So what is going on here? When the positive charge of nucleus increases, it provides stronger attraction towards the electron. But electron present in inner shell will almost cover the attraction or positive charge, or it will neutralize this positive charge mostly, so that outer orbital electrons feels less attraction towards the nucleus, because most of the attraction is neutralized by inner electrons. So let us say we have few electrons here. Let us represent these electrons as half arrows. So mostly these electrons will neutralize the positive charge of nucleus. That means attraction will be produced from the nucleus, but very few attraction sites or attraction will cross the first layer or inner shell. That's why let us say some of the attraction reaches to the outer side, and this less or lower attraction will be overcome, or it will be neutralized by the outer shell electrons. Okay, so most of the attraction is already satisfied by inner orbital electrons, and that's why outer orbital electron feels less attraction towards the nucleus. That's why they are loosely held with the nucleus. That means inner orbital electrons are screening the positive charge of nucleus. Okay, they are covering the positive charge of nucleus, and that's why outer orbital electrons feels less attraction towards the nucleus. So this is known as shielding of outer shell electrons from the nucleus by inner shell electrons, or in short we can say that this is shielding effect. When inner orbital electrons shields or covers positive charge of the nucleus for outer orbital electrons, it is called shielding effect. Okay, so due to the shielding effect, attraction towards the outermost electrons decreases, and removal of electron becomes easy. In case of metal, these type of situations are normal. You can easily observe these type of situation, and normal nature of metal is to release electron. One of the common reason for this losing of electron is shielding effect. Net positive charge experienced by the outer shell electrons is known as effective nuclear charge, Z effective. So despite the shielding of the outer electron from the nucleus by the inner shell electrons, the attractive force experienced by the outer shell electron increases with increasing nuclear charge. As we observed in image we discussed, suppose in this case this is our electronic configuration and this red line represents attraction or effective positive charge provided from the nucleus. So let us say we have second number principal quantum number and then we have third number principal quantum number. So our outer shell will be third number or 3 principal quantum number, inner shell will be 2 or second principal quantum number. So when we have comparatively less positive charge in nucleus, that means lower atomic number atoms, then we have comparatively less number of protons, that means less positive charge inside the nucleus. But let us say our second orbit contains all the electrons which it can be occupied. That means in second principal quantum number you will get 2s and 2p. So maximum number of electron in 2s it will be 2 and in 2p it will be 6. So total number of electrons 8. So all of these 8 electrons are already present in. Okay, so now no more number of electrons can be added in second principal quantum number because it is already full. Now if we move from lower atomic number to higher atomic number atom, so what will happen? Number of proton inside the nucleus will increase. Okay, suppose in this case initially we have 8 electrons in second orbital and 1 2 3 4 5 6 and 7 in third orbital. Okay, so total number of electrons 15. So same number of protons, obviously it will be present inside the nucleus, so we have 15 protons. Okay, so it represents phosphorus, so we have phosphorus atom here. So now let us move further. Let us talk about next element, sulfur. In case of sulfur, number of protons will be 16 and number of electrons obviously it will be 16. So what will happen? Extra electron will be added inside the third principal quantum number, not in 2 because 2 is already full with 8 electron. So now we have to add one more electron in third orbital and at the same time one extra proton will be added inside the nucleus, so one more attractive site will be observed. So as mentioned earlier, most of the charges will be neutralized by inner shell, but some of the attractive site will reach to the outer shell. So initially let us say we have this much attractive sites reaching to outer shell. Now we add one more proton, that means already capacity of second shell or its inner orbital is already complete. Okay, it cannot neutralize more positive charge because it has fixed number of electron. We cannot add more electrons in it. Okay, so it is already at its maximum. So added extra proton will attract outermost electron. That means outer shell will feel more attraction as the number of protons increases in inertia at the nucleus. In other words, the energy of interaction between the nuclear and electron decreases with the increasing atomic number. Okay, so that means because of neutralization, energies decreases. Both the attractive and repulsive interaction depends upon the shell and shape of the orbital in which the electron is present. For example, electron present in spherical shape, that means s orbitals, shields the outer electron from the nucleus more effectively as compared to electron present in p orbital. Spherical shape gives equal attraction from all the sides because of spherical shape. Similarly, electrons present in p orbital shields outer electron from the nucleus more than electron present in d orbital, even though all these orbitals are present in the same shell. Depends on the shape. Okay, so spherical shapes gives comparatively more proper shielding effect than p orbital. They are called dumbbell shape, and dumbbell shapes or p orbitals gives more proper shielding effects than d orbital, which is called double dumbbelled shapes. Further, within the shell, due to the spherical shape of s orbital electron spends more time close to the nucleus in compared to p orbital electron, which spends more time in the vicinity of nucleus in comparison to d orbital electron. That means, suppose this is our nucleus, this is shape of s orbital. As we know, it is spherical. So most of the time electrons are present inside this sphere. Okay, so that means they are always close to the nucleus. In case of p orbital, what will happen? As mentioned earlier, shape of p orbital is like dumbbell shape, so it will spend some time closer to the nucleus, but sometime it will be away from the nucleus. Why? Because if sometime electron is present here, then it will be closer to the nucleus, but if it is present here, then it will be away from the nucleus. It will be comparatively far than the nucleus of the electron of s orbital, like this. Okay, so this is the maximum possible range of s orbital electron. So as we can see, if electron is present within this range, then it will be closer, but if it is present out of this range, then it will be away from the nucleus. But possibility of electron present in p orbital is either upside or downside in case of p orbital, but in case of d orbital, as we know, it is double dumbbell shape, like this. Okay, so and let us say this is the area of s orbital of the same principal quantum number. So if electrons are present within this area, then they are comparatively closer to the nucleus, but if they are present in outer region, then it is away from the nucleus. So in case of p orbital, electrons may increase their distance either in upside or in downside, but in case of d orbital, they can go upside, downside, as well as left and right side. Okay, so as we move from s to p and p to d, most of the time electrons are moving away from the nucleus. In case of s orbital, they have limited space, that's why they are closer to the nucleus. In case of p orbital, distance is increased. In case of d orbital, it increases even more. So s orbital electron spends more time closer to the nucleus. Then we have p, and then we have d. D orbital electron spends less time closer to the nucleus, and same trend will be observed for f. F electrons will spend even less time closer to the nucleus. So because of this, Z effective or positive charge observed from the nucleus decreases with increasing azimuthal quantum number. Because if L is equal to 0, it represents s orbital, it represents electrons are closer to the nucleus. But if L is equal to 2, then it represents d orbital, and it represents electrons are mostly away from the nucleus. And effective charge, Z effective, is directly related with distance. Simple example, you can take the example of magnets. Suppose you have two different magnets. First you place them 1 centimeter apart. Okay, so obviously they will attract each other and attraction between them will be strong. Now put them 5 centimeters apart. So as the distance increased, attraction between them will decrease because they have a limitation of attractive area. If you place them 10 centimeters apart, then they are very less likely to attract each other. And if we place them, suppose let us say 5 kilometers apart, then no attraction between them whatsoever will be observed, because attraction is directly related or proportional with distance. As the distance increases, attraction or even repulsion decreases. Okay, attractive and repulsive charges are directly proportional with distance. So as mentioned here, as we move from S to P and P to D, we are actually spending more time away from the nucleus. That's why attraction between them decreases and Z effective decreases with increasing quantum azimuthal quantum number. And decreased attraction, that means decreased strength. So S orbital electrons are strongly bonded with the nucleus and d orbital electrons are weakly bonded with nucleus. And stronger attraction and more bonding, that means more stability, and weaker attraction and less bonding represents higher energy. So this is the reason, second reason, why s orbitals have lower energy than p orbitals, and p have lower energy than d, and d have lower energy than f. First reason was number of electrons. With the increasing number of electrons, repulsion increases. And second reason is distance. Because of increasing distance from L is equal to 0 to L is equal to 3, attraction decreases. Attraction towards the nucleus decreases. Okay, repulsion increases and attraction decreases. Both these factor increases the energy. Since the extent of shielding from the nucleus is different for electrons in different orbital, it leads to splitting of energy levels within the same shell or same principal quantum number. That is, energy of electron in an orbital, as I mentioned earlier, depends upon the value of n and L. Okay, so first thing, energy depends on n value because n represents, suppose this is our nucleus, this will be first principal quantum number, this will be second, this will be third. So as we can see, with increasing value of n, distance from the nucleus is increasing. So obviously if distance increases, then neutralization decreases, and that's why energy increases. That's why energy depends, or it is directly proportional with principal quantum number n. So now what happened with L? So we are using example of same principal quantum number. Let us say we are using n is equal to 3. So in n is equal to 3, we have 3s, 3p and 3d, 3 possible orbitals. So suppose this is our nucleus having positive charge, so this will be our first s orbital. So most of the time electrons will spend time closer to the nucleus like this. Okay, then we have p orbital. So this will be the shape of p orbital. If electrons are present maximum up to this line, then they are closer to the nucleus, but sometimes they may also present in this region. So that's why they are away from the nucleus. Most of the time they are not as close to nucleus as s orbital. And in case of d orbitals, this will be our situation. Sometimes electrons are closer, but most of the time they will spend more time away from the nucleus. Okay, so this is the first reason. Distance from nucleus increases as the L value increases. If L is equal to 0, it represents s orbital, then distance will be least. L is equal to 1 represents p orbital, so it represents higher distance. Then we have 2, that means d, and 3, that means f. So as we move from 0 to 3 for L value, it represents more and more time electron will spend away from the nucleus. That's why less attraction and higher energy. Second thing is repulsive forces. Okay, so this reason directly related with the attraction from electron and nucleus or protons. Our second reason is repulsion between the electron. In s orbital, maximum number of electrons possible is 2. For p it is 6, for d it is 10, and for f it is 14. So as the number of electrons increases, repulsion increases. More repulsion, that means more energy. So these two reasons represents why energy also depends on azimuthal quantum number. Mathematically, the dependence of energy of orbitals on n and L are quite complicated, but one simple rule is that lower the value of n plus L for an orbital, the lower is its energy. If two orbitals have the same value of n plus n, then orbital with lower value of n will have the lower energy. So this point is mentioned in table 2.5. So let us discuss table, and then you can compare the situation mentioned in figure 2.16b. Okay, so let us start with orbital 1s. So n value it will be 1, and L value will be 0 because S represents 0. So N plus L will be 1. Then we have 2S, so 2 plus 0 is equal to 2. Then we have 2P, P represents 1, so 2 plus 1 is equal to 3. Then we have 3S, again 3 plus 0 is equal to 3. So here we have common thing or common N plus L value. So in case of 2P we have N plus L is equal to 3. In case of 3S we have N plus L is equal to 3. So as mentioned earlier, here we have 2P and 3S. So 2P has lower value of N than 3S. Principal quantum number of 2P is lower, that's why it will be lower in energy. If N plus L is same, then concentrate on N value. Lower N value represents lower energy, higher N value represents higher energy. If N plus L values are not same, then no need to concentrate on N values. That means principal quantum numbers. Let us move so our points will be clearer. So 3P is equal to 4 and 4S again it is equal to 4. So obviously 3P has N value 3 and 4S has 4. So lower energy will belongs to 3P. Now 3D and 4S, concentrate on these two. So as we can see, for 4S N plus L is equal to 4 and for 3D N plus L is equal to 5. So just follow N plus L rule. Lower energy belongs to 4s orbital and higher energy belongs to 3d orbital, because N plus L of 3d is 5 and N plus L for 4s it is 4. So no need to concentrate on principal quantum number. Just concentrate on N plus L value. Higher the N plus L, more will be energy. Lastly, if it may be mentioned here that energies of orbital in the same subshell decreases with increase in atomic number. That means when we are moving from lower number atom to higher number atom. For example, energy of 2s orbital of hydrogen atom is greater than that of 2s orbital of lithium, and lithium is greater than of a sodium, and so on. So simple relation is mentioned. Energy of 2s of hydrogen is more than energy of 2s of lithium, it is more than energy of 2s of sodium, and it is more than energy of 2s of potassium. Why? Because as the number of protons in the nucleus increases, it provides more stronger attraction towards the electron, and stronger attraction represents more stability, and more stability, that means less energy. So in case of hydrogen we have least number of protons, that's why least neutralization occurs and higher will be energy. In case of potassium we have highest number of protons for given example, so that's why it provides stronger attraction towards the 2s electrons, and stronger attraction represents more stability and less energy.